So basically, if I have two Hilbert spaces, HA for system A and HB for system B, then the joint system is equal to HA cross HB. And so if I have some state psi in HA, some state phi in HB, then the joint state, we'll call it chi, an element of HA cross HB. And if we have an orthonormal basis for HA, let's just call it A sub L. And likewise, an orthonormal basis for HB, we'll call it B sub K. Then we can construct an orthonormal product basis for H as follows. Our basis would be A sub L cross B sub K for all choices of L and K. So L runs from 1 to the dimension of HA, K runs from 1 to the dimension of HB, and so here okay, and so a state in H of the form omega equal to psi cross phi is a product state and an arbitrary state chi in H admits the following decomposition. Chi is equal to a sum over L and K. Let's say it's CL comma K, AL cross BK. So a state of this form is a special case of a state of this form. So in general, states of this form can be entangled. Sometimes you'll write down the state this way and it looks like it's entangled because it doesn't have this form, but a change of basis will reduce it to this form. Someone has the open question, well, it's so closed question now, but one has the question, how can I tell if this state admits some choice of, admits this form? So in general, chi can be entangled. In particular, we say that chi is entangled if it does not admit does not admit an expression. It's not the best way to say it. For some phi, for some psi in HA and phi in HB. Okay, I have a lot more to say about entanglement, but before I start talking about entanglement in depth, I want to introduce two things to you. One is I want to review representations of quantum states. So a representation is we go from the abstract identification of the vector as just some vector in the Hilbert space to actually writing down a column vector that's associated with choosing a basis and expressing the state in that basis in terms of its expansion coefficients. And then I also want to introduce density operators. So I want to talk about the reason why we talk about states as projectors rather than vectors, and how we can account for mixed states. And then we'll be able to talk about entanglement. So in the context of representation, I'm expecting this to be basic review for all of you. If it's not, then you should spend some time becoming very familiar with this, but I just want to recap and make a point. So, given a choice of basis, for HA, and here I'll just stick with the one I've chosen already. You can always write psi is equal to sum over L, psi L, AL. And then we have a representation of this as a column vector with components, so L starts at 1 and goes up to the dimension of HA. And then I just write down my coefficients. Oh, sorry, it's bad notation. Psi 1, psi 2, all the way down to the dimension of HA. So that's a representation, and it's a basis-dependent concept. Similarly, for HB, we have phi can be expressed as an expansion with respect to a basis. Here k goes from 1 to the dimension of HB, and we'll use phi sub k bk. And then we have a representation of phi as a column vector, phi 1, phi 2, ... Where, of course, these guys, each phi sub k is equal to the inner product between the dual vector. So bk is an element of a basis for HB. The bra is its dual, the dual vector, which is actually a linear functional acting on the space. And here we're seeing it in action. That linear functional is going to act on phi and return a complex number, which is our coefficient in that basis. And similarly here, we have the identification that psi L is defined as the dual vector AL acting on the vector psi. And this is a linear functional, so it acts on elements of the Hilbert space and returns a scalar. And here the linear functional is exactly in one-to-one correspondence with the original vector itself because of Rietz's theorem. And that's how we identify these coefficients. And now the tensor product the tensor product expressed in the representation then is the form we have psi tensor phi gets represented as psi 1, psi 2 cross phi 1, phi 2, which is equal to a composite vector. And now I'm going to make a convention choice. You can choose whatever convention you want. The convention I use is that the rightmost object in the tensor product varies most rapidly. So I'm going to call this psi 1, phi 1, and this is just a regular multiplication. This is psi 1, phi 2, and then we go down to psi 2, phi 1, psi 2, phi 2, and hopefully you all see the pattern. Now I could have done it otherwise. I could have made this psi 1, psi 2, and kept these guys as phi 1. Okay, so this is the most common convention, but it's just a convention. As long as you stick to your convention, you don't make mistakes, right? So here, each of these elements of my composite system is, this is just, each one is, of course, a complex number. And it's the product of the two complex numbers here. Now, last lecture, I discussed in some depth the analogy. So, I mean, certainly in my case, and I think for many people, when they learn about this tensor product structure of quantum mechanics, it's very new, it's very exotic. The point I was trying to make last week is that it's not new and it's not exotic. It's something you already know. So if I have consider in the case, so I'm just reiterating the point I made last class, but in the context of representation, it'll be clearer. So suppose I have two events. I have a probability. Instead of suppose, let me write consider. So I have two dice. Here, let me just give a heading. So analogy to classical probability. You know, I have some die here, and it has 6 sides. Okay, oh, this one's a 2. So this is die A, and then I also have die B. These dice can be different, can have different numbers of sides. It doesn't really matter. You know, etc. Okay, this is die B, and I say the probability, I have a probability vector associated with each face of the die. So I have probability P1, P2, all the way down to P6. And here I also have another probability vector associated with the second die. So these are in general biased. So they need not be uniform probabilities. They can be arbitrary. And now I want to say, what's the joint probability of getting a 2 on this dice, this die, and getting, say, a 3 on that die? So I can talk about the joint probability of one outcome on each die. Okay, and so I can use the same indexing here. Let me use the index L. Goes from 1 to 6. And here K goes from 1 to 6. And then the probability of both dice, then I have the probability of both dice is given by the tensor product of these two vectors. Okay? So basically, you know, the joint probability vector is equal to P1, P2 times Q1, Q2, which just gives me this same thing we have over here, just P1, Q1, P1, Q2, P1, Q6, P2, Q1, and so on. So what's the probability of getting outcome 2 here and outcomes 1 here? Well, it's right here. It's this product of each probability. Okay, so we see that the tensor product symbol is just exactly what you would expect from probability theory. So again, this reinforces this notion that thinking about quantum state vectors as probabilistic objects that describe our incomplete information is a very helpful way to understand why the structures of quantum theory are the way they are. Okay, so that's kind of a conceptual point, and I just want to emphasize that taking this point of view seriously does not imply that you have to believe in hidden variables. There's a nuance there. When I say quantum states are states of incomplete knowledge, there's 2 ways to finish that sentence. Okay, the most conservative way to finish that sentence is to say it's incomplete knowledge about the outcomes of future tests I might perform on the system. That's very operational, right? So certainly one of the things we learn from quantum mechanics is that we have uncertainty. We have uncertain knowledge about the outcomes of some tests. So in a sense, it's just a completely orthodox statement to say that quantum states are states of incomplete knowledge. But traditionally, a statement like that is used to motivate an interpretational point of view, which is that it's not only incomplete knowledge about the outcomes of future experiments, of future measurements, it's incomplete knowledge about some underlying reality. And then when you say that, you're exploring an interpretational notion. So both of those, I think that this insight, this analogy to classical probabilities with quantum states is consistent with both of those ways of thinking about incomplete knowledge. Okay, so now we'll set that aside and start looking at more general issues in representation. So in particular, I told you how to construct the representation for the composite state when the composite state is a product state. But in general, the composite state is not going to be a product state. It will be an entangled state of this form. And then how do we construct the vector? How do we construct the column vector representing chi? So in general, given some chi, which is equal to sum over Lk, CLK, AL, tensor BK, then just the representation is just written already in our answer. It's just C11, C12, and so on. C21, C22. Now, before I start telling you about how to identify entanglement, how to develop criteria for entanglement, let me first tell you a little bit about density operators. Okay, so axiom one told us that we associate the quantum state or the preparation, ideal preparations, and of course the shorthand way to refer to that is just to call it a quantum state. Ideal quantum states are rank 1 projectors. Okay, acting on a Hilbert space. This is just a quick summary. And why do I want to talk about projectors here? I'm talking about states as Hilbert space vectors. And of course, then the point is given some chi, I can construct the state, the quantum state operator by just taking the vector and its dual. So we'd call this rho. So here we call it a quantum state operator. All right, and it's this, we call this an outer product. Which in this case, which is a projector. So the term outer product allows the arguments on each side to be different. So you could have, chi and omega. Then it's not a quantum state because it's not a projector. So it's a projector when you have the same element in the vector and its dual in this outer product. Okay, so this is our state. Now, what about non-ideal? What about non-ideal states? So these are very important. I have the thermal state of some solid, or of a cavity, for example. Yeah, there are lots of contexts where you want to describe the state where you don't have the maximal knowledge allowed that's possible. Okay, so there's going to be two paradigms. Two paradigms that require more general kinds of state operators. Okay, so the first scenario is this. Let's just imagine I have a device that spits out. Suppose I have a device that prepares the state chi1. Well, let's do this in full generality. So it prepares the state chi-I with probability pi. How do I describe that device? Okay, if it's a thermal device and these states are energy eigenstates, then this probability will be given by the Boltzmann factor, e to the minus kt. E to the minus energy eigenvalue divided by kt as the weighting. All right, but in general, you can have an arbitrary weighting. So then let's look at our recipe. So using axioms 1 and 2, given preparations, then we say, okay, well, here's our situation. We get outcome probability. So now let's assume an arbitrary measurement. Assume a measurement of an operator A, which has spectral decomposition sum over L. I think I'm using AL for my basis. That probably doesn't matter. Let me just call it lambda L, AL, AL. Here, let's call this AL. All right, here I'm assuming it's non-degenerate for simplicity. More generally, I could write this as just an arbitrary projector. Now, if I use this section of the board, is this kind of hidden from how low can I go? Let's see about this. Oh my goodness. All right, I got to think these things through in advance before I say them. All right, so outcome probability for case I. Well, Born's rule says the probability of outcome AL is equal to the trace of chi I against the associated projector AL and so we know the answer. We know the probability of this outcome when the device prepares I, state II. But we don't know if it prepared state I. We just know the probability with which it prepared state I. So clearly, the probability of outcome AL not conditioned on I and here I'm reaching the limit. All right. Okay, so to be continued. Here, you know what I'll do? I'll write it down and then I'll move the board up. Probability AL not conditioned on I is the probability of AL is equal to a sum over I, the probability of preparing case I times the probability, so actually I wrote this wrong. This would be probability of AL conditioned on I here. Then we have the probability of AL conditioned on I. And then we can write out what that means. Sum over I, PI, trace of chi I, AL, AL. And then the fact that the trace is a linear operation means that I can bring the sum inside the argument of the trace. So then I can write this as the trace of sum over I, PI, chi I, times AL, AL. So now what we're going to do is we're going to identify an object rho, which we're going to call a state operator, as the sum over I, PI, chi I. So it's a probabilistic combination of the rank 1 projectors. And so we're going to call this a density operator. And it's going to be our general notion of state. All right, so in particular, we have the following. A general quantum state / preparation is a density operator. A density operator so a general quantum state or preparation is described by a density operator. So the physical thing, the experimental object, is associated with this mathematical object. What is that mathematical object? That mathematical object is defined as follows. A density operator is a non-negative non-negative linear operator add normalization, satisfying a normalization condition that the trace of that operator is equal to 1. And this is going to preserve probabilities. This is, well, the fact that it's a non-negative linear operator implies that it's Hermitian. Because remember, Hermitian, it means that the eigenvalues are real. Non-negative means that the eigenvalues are real and non-negative. So let me just give you a non-negative linear operator call it rho, satisfies psi, rho, psi. Now here, psi doesn't stand for the state. It just stands for some arbitrary vector in the Hilbert space. X? Maybe X. No, I don't like X. How about here, omega? Okay, so this is not non-negative for every omega in the Hilbert space. So a linear operator acts on a Hilbert space. If it returns a non-negative number for all vectors in the Hilbert space, we say it's a non-negative operator. Note that in particular, this implies that the eigenvalues are all non-negative, and which follows from just considering omega to be the eigenbasis of rho. Yeah?
But don't you also need to stipulate that rho is always diagonalizable? Don't you need hermiticity then? Or
okay, how does this work? Yeah, so I knew this at one point, but somehow it's sufficient just to call it non-negative. So we know it's a linear operator that doesn't guarantee diagonalizability. When you say it's non-negative, you're making this statement. And if I recall correctly, this is strong enough to imply that it's diagonalizable. Because certainly Hermitian implies diagonalizable, and non-negativity implies Hermitian.
I thought this was the definition of non-negativity.
Well, often people say it, but I think it's redundant. So maybe that's something that's, I'm fairly confident that's correct, but I can't remember the justification. So if one of you cares to look that up and get back to me, that'd be great.
The fact that it's Hermitian just says that your eigenvalues are real. Doesn't say if they're positive or not.
Right. But what he's suggesting is that non-negative isn't strong enough to guarantee diagonalizability. When I'm claiming that it guarantees that eigenvalues are non-negative, I'm claiming that it's diagonalizable. So somehow non-negativity should imply...
Non-negativity is not the same as saying it's Hermitian.
No, it's not the same. Okay. It's stronger. So what I'm claiming is the following, is that you have your linear operators, and then you have normal operators, which normal operators satisfy A dagger equals A dagger A. And then inside that, you have Hermitian, which is that A equals A dagger. And then most people don't know this, but inside of that, you have self-adjoint. So there are Hermitian operators that are not self-adjoint. And that only happens in infinite dimensional Hilbert space, that distinction exists. Self-adjoint operators have the condition not only that I think this is the way you write Hermitian. This is self-adjoint is this condition, and Hermitian is the condition that what is Hermitian? Hermitian is the condition that the conjugate transpose equals itself. But wait, all right, let me just check my notes. I can't remember. No, I have it here. Let me just look it up. I can't remember now how the. Wikipedia and truthiness. You think Wikipedia knows quantum mechanics better than I do, huh? I doubt that's the case. But no, I mean, granted, this is something I'm not 100% certain of, so I'm just teasing. Let me just check my... Where is this? It's right here. Oh, I see. I'm missing a page. That's what's wrong. 9, 10... Here we go. Right, okay. Hermitian is the condition that A phi psi is equal to phi A psi for every psi and phi in the domain of the operator. Okay, this domain issue is an issue you have to deal with when you're dealing with infinite dimensions. And then self-adjoint is more complicated. So self-adjoint is defined by the condition A dagger A, and it implies two things. It implies one, or it's equivalent to two conditions, rather. One, that it's Hermitian, and two, that the domain of A is the same as the domain of A dagger. And again, the possibility that these two things are not equal only happens in infinite dimensions. So in finite dimensional quantum mechanics, Hermitian and self-adjoint are equivalent. In infinite dimensional Hilbert spaces, they're not equivalent. There's a stronger condition for self-adjointness. Okay, and so that's why this self-adjoint circle is inside the Hermitian circle. And then inside of that, we have non-negative. And actually, I don't know if non-negative also reaches into this or not. So let me just draw it this way just in case. Okay, and diagonalizability is guaranteed by virtue of the fact that it's normal. Oh, geez. I think I lean up against the chalkboards is the problem. Oh, God. All right. Okay, and then let me just confirm. So here's a bonus question. Verify I guess maybe the conditions under which non-negative implies Hermitian and if I'm right, update Wikipedia. if appropriate. Of course, we can make it true by just updating Wikipedia without checking. And that would be in the fine tradition of Stephen Colbert. Okay. All right, good. So next is case 2. So I was talking about non-ideal quantum states. And case 1 was this kind of ad hoc scenario where we have a device that's preparing different states with some probability. It sounds very contrived. So now there's a much more relevant scenario that's also much more interesting where you get density operators. And that is when you have a composite system that's entangled, and then you ignore one of the two systems, and you just want to describe one of the two subsystems. And we're going to see that a pure state of the composite system induces a mixed state or a general state operator of the subsystem. Yeah.
Small thing. When you say it's entangled, can you be specifying entangled with respect to some partition? Because you have two systems, HA and HB, but both HA and HB can have different degrees of freedom, right? Where I can have my states entangled in each of those subsystems for each degree of freedom.
So normally what happens is that the tensor product structure that's relevant is prescribed by the problem, and it's a given. And it doesn't even make sense to start talking about whether the systems are entangled or not until you've made some decision about what the structure of your system is. And so, yeah, so you don't worry. You assume the first step is tell me what the tensor product structure is. Then I can talk about entanglement. So if you have a tripartite, so an example where that's important is suppose you have a tripartite system. So I have 3 spin-half particles. And I want to talk about the bipartite entanglement between 2 factor spaces. Well, I have to decide how to chop that up. I have system A, B, and C. I can talk about the entanglement where I take A and B to be one system, and how are they entangled with C, or vice versa. So yeah, but that's in the background, and that's a background assumption. You know what? If someone asks for breaks, so I just want to clean my pants because I feel silly, so I'll just go do that and maybe grab a coffee, and then we have like 3-minute break. Okay? Should probably turn off my. I can prove that I've worked out the proof that positivity or generally that expectation being real is
It's sufficient for diagonalizability?
It's sufficient for permission, which is sort of sufficient for diagonalizability. You need additionally, so if you also impose that the trace is 1, then that means that it's what's called a compact operator, which necessarily and a compact permission operator has.
Well, I mean, we can even do it in finite dimension, though.
What? Oh, okay, yeah. If it's if the expectation is real, then it's permission, which in finite dimensions means that it's diagonalizable.
But in infinite dimension.
In infinite dimensions, you also need the trace equals 1.
Right, but does non-negativity implies relativistic or
yeah.
something?
The idea is expectation of if expectation of u and tu is real, then it equals its transpose
which is the expectation value of TU of U. By definition, that's the expectation. That's the inner product U of T dagger U. That means that T minus T dagger has the property that its expectation is always 0 by considering things in the form A minus B. You can use that to show that it is 0.
Right. Okay.
Yeah, that's good. I'll buy it. I wonder what everywhere.
But I
read
you
about it,
can
they
show- wait.
stipulate a regulated termination.
Wait, you're choosing your vectors in the inner product in the
Say,
domain of
not
the operator, right?
Right.
So that accounts only for permutation.
Well, it just automatically
But for
happens
self-adjoint,
when you take the outer part.
Self-adjointness also follows from the trace being. No, you don't. You need more than just the trace being 1. You do need positivity because then the trace.
At least in finance.
The trace equals 1 together with positivity implies that.
okay, but what you said is positivity means positivity implies
I would hope so anyways. I mean, otherwise, you guys don't even need me.
But
Just read Wikipedia.
does that imply that the domain
I don't know why, but every
A and
I don't know
are
why they
all
always
the same?
stipulate, like,
So,
every definition of non-negative operator stipulated.
Compactness. So in compactness or more weakly boundedness, which just I don't know why they had to find that. But the norm of bounded by some multiple. You gotta be careful. Be careful who you're choosing. It doesn't get most you have a positive.
I read it like mathematical definition of
Some people say this as an action after they say they have a Hilbert space.
But anyway, if you have a bounded, if you have a bounded permission operator, you can extend that to the entire state, the entire self-adjoint.
Can we get started, guys? Okay, good. So I was going down to the bistro after the lectures, and I kept noticing that my pants were completely covered in chalk, and I couldn't figure out why. And then I realized it's these things. I keep leaning up against them. Right, so we've solved that problem. All right, so now let's talk about the really interesting scenario, which is why we need density operators as a consequence of entanglement. So suppose I have systems A and B with the usual, I'm just going to use my standard notation. We have our Hilbert space HA cross HB, and we have our usual orthonormal basis. So now I have chi sum over L and K, CLK, AL, BK. And now I'm interested in, so that's the usual setup, but now here's the twist. I'm only interested in describing system A from now on. I am only interested in describing system A. Okay? So I have half of a interacting system, and I just want to describe that half. So basically, what does it mean that I'm only interested in system A? What it means, say, is that I'm only going to do measurements on system A, so I don't care about system B anymore. So suppose I only will perform measurements on system A. Okay, so that means my measurements are of the form A tensor identity, which is equal to the trace of chi times A tensor identity. Okay, so this is just matrix multiplication here. So, or more specifically, I might be interested in the probability of the outcome of AL. So this is OR. This is, in a sense, this is more precise, which is going to be the trace of, again, our preparation chi against AL tensor identity. So you should really start thinking of having identity on the second factor space, meaning that I do nothing to that system. Okay, so then we can look at the effective description we get. So we require assigning an operator rho A to system A such that all my predictions in this picture are reproduced. So in particular, what that means, I want for every A, which is a linear operator acting on HA, so this is equal to linear operators acting on HA. One of the conceptual things you have to get used to is that most of you probably learned quantum mechanics where you think of quantum states as vectors in the Hilbert space and measurements as operators acting on the Hilbert space. But now we're going to use a formalism in which the states themselves are linear operators acting on the Hilbert space, right? So in this picture here, where did I write down rho? Here. So here, the point is, for this piece here, we have rho is an element of the linear operator on, what's my Hilbert space here? It's just generic. It's a linear operator on some Hilbert space. That's why I call it a density operator, because it's a linear operator. So such that for every observable A, we have that the expectation of A given by the trace of rho A against A is equal to this expression here is equal to A tensor identity, where here implicit in this notation is this right-hand side here. All right, so let me call this star. Okay, so implicit in this is the state chi appears in this expression, and the state rho A appears in this expression. So we want a rho A, we want a state assignment for system A, which reproduces all the predictions where I just use my original state in the bigger Hilbert space, but do nothing on part of it. Okay, so let's find a density operator rho A which satisfies those criteria, that criterion.
So that defines rho A.
Yeah, basically it's going to define rho A for us. Okay, so let's recall, given some operator, given some rho, which is a linear operator on some Hilbert space, then we can construct its matrix representation. Its matrix representation is given by rho A 1, 1. This is a bit annoying having too many subscripts. I'm going to move my A to the top here so I can avoid clumsy notation. Okay, so this isn't general relativity where it matters whether it's a superscript or a subscript. For us, it's just an index. Okay, so so here we have row A11, row A12, row A13, row A21, etc. This is row A22, and so on. And here we have the definition that row ij of A is equal to, say AI row A aj. Okay, so this is our matrix representation of the linear operator. And just remember the right way to do this. So, oh yeah, so I noticed in my notes I have a nice notation where I actually, to emphasize that this identity acts only on B. This is, of course, implicit from our ordering of the tensor product, but so it's slightly redundant, but nice to put a little subscript B over here, just so we remember that as a reminder. Okay, so then we have A tensor identity on B is equal to that expression, and that's going to be equal to a sum over L prime K prime. Here I'm just writing out explicitly my trace operation. Now I insert the identity, right? So I'm inserting AL BK, AL BK. Just because I'm trying to confuse you guys, I mixed notation. So here I put a tensor product symbol, and these extra guys, and here I just drop them completely. You just have to get used to the fact that this is different ways of writing the same thing. So now what I did here is I'm summing over L and K. So so do you see what I'm doing here? What I've done is I've taken that expression, the star expression. When I evaluate the trace, that means I sum over an orthonormal basis. So I'm doing this. This is, sorry, I called this chi. Chi. And then I have AL prime tensor BK prime. So what I did is these pieces here are the trace. I'm writing it out explicitly. And then between chi and A tensor identity, which I think I had in the opposite order over there, but it's the same by the cyclic property of the trace, then I insert a resolution of identity, right? So we know that identity on AB, the identity operator on the big Hilbert space, so I've inserted identity here, is sum over L, K, AL, BK, AL, BK, right? So I inserted identity between chi and A tensor identity. And so now we get this, somewhat involved expression, which is a bit tedious to write out, but not all that painful in the end. And then we can write everything out in terms of the coefficients. So we're summing over L, K, L prime, and K prime. And we have A, L prime, L times delta K, K prime times rho LK, comma L prime, K prime. So here, here I'm calling rho equal to chi. This is rho AB. So chi was, I think that's what I used over there, chi. So here I'm just calling there's no hat here because this is a matrix element. So each of these guys are complex numbers. And I get a delta KK prime. Where did that come from? It came from the fact that in this expression, I have an identity here. And remember the rules we studied last class. here BK is a dual vector which acts on only things to the right of the tensor product, which in this case is identity. And so then it skips over that, and then it acts directly on BK. So BK is an orthonormal basis, so BK prime BK gives us delta KK prime. And then A, we have AL prime AL, and then chi is just a standard matrix representation of chi. And we're writing it this way. So we can think of this as just sum over L, L prime, AL prime L times the sum over K, K prime, rho AB, LK, L prime, K prime. All right, and then this piece here, we will define to be rho A, L, L prime, because I'm summing over K, K prime, so I lose the reference to those. So now the idea is let's take that. Let's assume that this is a matrix representation of our density operator rho A we're trying to find, right? And so then the point is we want to compare this to our desired expression, trace of A against some rho A. Right? This is what we wanted. And so if we write this out, we get a sum over L yeah, that's right. Thank you. This is just a K here, right? Thanks for catching that. That's important. Now, why do I have an L and L prime here? That's not obvious, but oh, right. So here we have a sum over LL prime, and we evaluate the trace by doing a complete basis, but now our complete orthonormal basis is just for system A, right? And then here we have an A, and then we're going to insert an identity. So this is the L prime part, AL prime, AL prime, rho A, AL. So this is evaluating the trace, and this piece is inserting the identity. And then you'll see immediately that what we get is exactly this expression. We have a sum over L, L prime, the matrix elements of A, AL, L prime, and the matrix elements of rho A, L prime, L, and that bothers me. Ah, they're dummy indices, perfect. All right, so we can just swap the meaning of these two. So we'll just do that. Good. Okay, so we've seen now that if we define rho A in this way, we recover what we wanted. So now I did this in a this is kind of a cheap way because I used the representation. It's always nice to do things just at an abstract or formal level. And so what we can do is, I'm going to move over here, and if this doesn't show, I'm sure it shows up. They've got so many cameras in here. All right, so the point is then, the upshot of this is we can identify rho of system A as what's called the partial trace over system B of rho. Where the partial trace is like the trace, but you only evaluate the trace on one of the systems. It's called partial trace, and in particular, so this is a period. So given some operator rho, well, here, I'll just write it out. So what we have is that trace Can you guys see here? Is this, yeah, this looks pretty good. Maybe you might have some trouble, but can you see it okay? Okay. Piece of chalk. So I'll just write it up here. So basically, the trace over system B of some operator rho, where here rho is a linear operator on HAB, which means HA cross HB, is equal to a sum over K BK rho BK. Okay, so this is essentially the definition of the partial trace. Yeah?
What properties does the partial trace conserve with respect to the properties of a normal trace over the whole space?
What does that mean?
For example, does the partial trace have the cyclicity property?
No. That's a common mistake people make, actually. So what the question was, can we just assume the partial trace has all the nice properties the trace has? For example, the cyclic property of the trace, which is that trace of A times B is equal to the trace of B times A. And the answer is no. Okay, so you have to be careful with that. Let me just remind you that whereas the trace of rho is a map that takes rho to, well, I probably should just make this a dot. So the trace of some object takes the input and it returns a scalar. It returns a complex number. So note, that's the full trace. The partial trace is an object that takes, actually, let me write this better. It takes a linear operator on the Hilbert space to a complex number. The partial trace takes a linear operator on HA cross HB and gives you a linear operator on HA. Okay? So it's a very different structural issue. So here, this is, you can think of this actually as a functional, and this is a different type of object. It takes linear operators on a bigger space to linear operators on a factor space of that bigger space. Okay, but what it is, it's for us, the partial trace is the way to construct the state of a subsystem when all you know is the state of the full system. And so then it's an exercise to realize that the set of objects you obtain via this rule, this partial trace rule, is actually the set of non-negative operators with trace 1. So the important point here, which I'll write down as soon as I say it, is that we considered case 1 somewhere. Case 1, which is we imagined that we were preparing different states with different probabilities. And what we obtained was an effective description of that in terms of in this language. We found that we needed quantum states which were density operators, which mean they're non-negative linear operators satisfying trace rho equals 1. When we worry about this situation, where we get states describing subsystems, you find that the class of objects you get via the partial trace acting on a valid density operator, a valid quantum state in the bigger space, is you get another density operator on the smaller space. So here's the point I want to make, and I don't know where to write it. Write it here. Point is that the set of objects rho A obtained via partial trace is the set of density operators. So the one thing that's a remarkable fact about quantum mechanics is that if I give you a density operator, I give you a physical system, and you can do any measurements you want on that system and learn everything you possibly can about that system by learning everything you possibly can about its density operator. It is impossible to tell whether the mixed state came from part of an entangled state or via this method 2, or whether it came from method 1 by mixing together pure states with some apparatus like I described here. I'm sorry? Well, yes. Well, I mean, I think that's not obvious because consider a spin-half particle, right? So I have some coherent superposition of the two levels. All I need are classical resources to prepare different pure states and mix them together. But think about doing it in the lab. It's very different. The requirements are very different. So preparing a mixed state via just mixing together different pure states you've prepared of your single spin-half particle is easy. Creating a mixed state of a spin-half particle via first entangling that spin with some other spin and then ignoring that second spin, that's hard. So the first thing they could do for 60 years ago, and the second thing they can only do for about 15 years now. Well, that's not quite right. For spin-half particles, yeah, maybe. For photons, they've been doing it since the 70s. But the point is, the experimental requirements for those two things are very different, but yet the class of objects you get are the same. And it is, in a sense, a philosophical point, because the point is, a priori, it's not obvious that the class of objects you get will be the same under those two experimental approaches. But it turns out that they are the same, and that it's indistinguishable. And the point is, that's not the case for measurements, and that's not the case for transformations. So there are transformations you can do in the lab via mixtures of unitaries, and that gives you a set of possible transformations you can achieve. But there's a superset of that, which is the set of transformations you can realize when you act the unitary on a composite system and then ignore the composite system. You get a bigger class of transformations that you can achieve that way. So in other words, states, what you're wondering is if it's a trivial identity. It is trivial for states, but when you go to transformations and measurements, it turns out these two classes are different. So it's actually kind of an interesting distinction. But you can only appreciate that once you understood these other cases, I guess. There's a few more things I wanted to say, but I guess I don't have time. But let me just tell you where we're going. So now that we have these tools, we're going to start talking about entanglement, and then I think we'll just talk about Bell's theorem maybe earlier in the course than traditionally. And then I'll discuss some of the infinite dimensional Hilbert space issues, and then continue with the outline as planned from there. But before we wrap up, do you guys have any questions about this this structure? And did I leave anything hanging?
So you did this for pure states, right? Did you realize it's immediately for mixed states?
Yeah. So instead of calling rho chi, in other words, if I have some mixture on the big space, then I still get. So this claim I made here that the set of objects you get under partial trace is a set of density operators, that's true as long as this is a density operator. As long as the input is a density operator, the output is a density operator.
Guarantees that the resulting thing won't be a pure state.
That depends. So it depends on if I have a product state of A and B. Actually, this is a good exercise. Let's just work through that, because
a non-entangled state,
yeah.
And you take the partial trace, it's a pure state.
Right.
That immediately says your state was entangled before. But in general, if you take an entangled state, then the new density will be mixed.
If rho is equal to psi cross phi, then rho A, which is equal to the trace over B of rho, is just going to be equal to psi, which is a pure state. You can check this. So in fact, what we're hinting at here is a test for entanglement. So if I have a state on two systems and I want to know if it's entangled, how do I do that? Well, what I can do is I can just look at the subsystem, rho A, and I can check if rho A is pure or not. And if I'm promised, here's the trick. If I'm promised that the state of the joint system is pure, then the state of the subsystem will be pure if and only if that state was unentangled. But here's where we already reached. This is something I'm going to talk about next lecture, by the way, but I'm just previewing it. When you go to mixed states, so if rho is a mixed state, so it does not admit an expression of this form. I haven't even rigorously defined pure and mixed for you, so I'll do that. Then it turns out this test doesn't work anymore, because you can have a mixed state of rho A even though you just have a mixture of unentangled states in the full space. And it turns out this is an interesting question because this is a major unsolved open problem of quantum information theory. If I have an arbitrary mixed state of two systems, how do I decide if it has entanglement? And basically, we only have a partial answer to that question. And so this is, a challenge to you guys that's something that, I think that's a solvable problem, and no one's figured out how to solve it.
So you define what is to be entangled or not for a pure state, right? You're saying that for mixed states, there's no clear answer of how to define what is when does a mixed state is not entangled or not. I mean, if I take a density matrix that I can write as the tensor product of two density operators, that's unentangled, right? But can you have a mixed state that cannot be written that way and be entangled as well?
No. So what you're asking is what I'll do next lecture. So let me give you the precise answer next, but the answer is no. All right, so pure states are defined by three equivalent conditions. This is something I should tell you right away. So a pure state rho, a state rho is pure if rho is equal to psi for some vector in the Hilbert space. A state rho is pure if you take the square of it and it's equal to itself. And thirdly, a state is pure if and only if the trace of rho squared is equal to 1. So somehow it looks like this is a stronger constraint than this. Notice there's a 2 here. This is a square. It's a very small font. Sorry about that. But these are actually equivalent because we're working in the context that rho is a non-negative operator. And so that actually makes these two conditions. These two conditions would not be equivalent for an arbitrary linear operator, but for a non-negative operator, they're equivalent. So this is what I mean by a pure state, right? It basically means that there exists some projector, rank 1 projector. And typically, if you want to calculate something, you just calculate trace of rho squared, and you check if it's equal to 1. And if it's not a pure state, then it's a mixed state. I'll recap this next lecture. I just wanted to make sure those terms were clear for all of you. OK, thanks again for your attention, and we'll see you tomorrow.